roll over some admin stuff. So looking to the future, homework 14 and 15 lab 5 are due next Wednesday. Lab 5 should have gone up yesterday in the all students. I will make an assignment of it today. We have and make sure you take advantage of this week getting ahead, because we have lesson wise, we are relatively light this week. So lessons 14 and 15 are they're really two parts of the same thing. They are very conceptual. I say light, it's still some really, I just mean light in the sense that not a lot of like heavy mathematical work, but it is, I'm taking the two lessons to do it because it is kind of foundational and understanding. So take the opportunity to work on your labs and homework, but also to really understand what we're talking about, because it's literally going to be, I know I try not to use like, ominous words, but it's literally the foundation of what we're going to be doing. The rest of the semester, we are going to be doing more or less the same thing, just different versions of it. And it's all going to be based off of the reason we're allowed to do it all is based on what we're doing today and Thursday. Okay, that's going into the future. Going to the past a little bit, we had the GR last week. From my standpoint, it went pretty well. I know some people didn't get necessarily what they wanted. Some people had some questions, and we can definitely go into that. I think last I saw, the average was around 77. I got to check to see if it went up or down. There are still a good handful of people who need to take the makeup this week. I am going to figure out today when that will be. But we had more people than I thought who needed it for different SCAs and different things. So I just need to find a time this week, or a window at least, that is good to accommodate most, if not all, of those people. So I will be contacting the people who needed to do the makeup to let them know what the options are for this week. That said, if anyone has any questions on how they did on the GR specifically, just set up a meeting with me. Each person has a slightly different version of the GR, so I just need to open it up between the two of us, and we can scroll through and see what you missed, what you didn't, and go through anything that you want to look on that. That said, if you want to do that this week, I ask that you set up a time with me Wednesday or Friday, because I am down an instructor this week. I don't know if any of you have worked with Captain Forbes. He's a great guy. He's my ACD, but also one of my instructors. He is out this week, and so I am taking over his courses. So I'm actually teaching M1 through 7 today and Thursday, which is fine. It just means that I am don't have a lot of free time on M days this week. That being said, if you do need EI, or your only time is on it, you can either send me a message and I can try to answer it, or the other instructors are all available for most of M days. Colonel Barger, Colonel Columbine, Dr. Holloway, and Colonel New. If you guys need any contact information, let me know, and I can set you up with them. I'm also with an instructor and assistant down. I'm a little behind on labs, and so I apologize. I am going to do my doggonest to get through the labs today and tomorrow to get them back to you guys, because I should have last week, but a lot of things just fell apart, and we all came out good. I just am behind on grading. I also need to get your grades into KIMS, which is another promise I'm going to try to keep to do today. Okay, so those are all the things I owe you and what we are working on. Any questions that you guys have from last week or going into this week or next week before we get into the meat of today's lessons and stuff? All right, okay. So today's lesson and tomorrow's are on this idea of sampling distributions and the central limit theorem. But I'm going to kind of come at it sideways today and show you some things, because I really want you guys to, we really struggled with this in a lot of my sections last semester of understanding this. So that's why I'm taking 2 days this semester to go over, because I really want to make sure this makes sense to you guys. So let's use a real simple concept of flipping a coin. And I think we've all decided that we have agreed that we are not going to talk about my handwriting and how it sucks. So at a real high level, the difference between last block and this block is that last block was focused on probability. This block is focused on statistics. And I know that a lot of times in course descriptions, we say them in one breath, right? We say, what are you taking? I'm taking probability and statistics. And it makes it sound like they're the same thing, right? But they're very similar, but they're also very different, right? So probability is talking about predicting future events, right? Like flipping a coin. So I say, hey, based on probability, there is a 50% chance that this coin is going to be a head, right? And so I have calculated probability and said, hey, there's an equal chance of each one happening. And so when you flip this coin, I predict that 50% of the time it will be a heads, right? That's the whole point of probability. Statistics goes in the other direction, right? Whereas probability predicts future events, statistics basically analyzes past events, right? So statistics is something along the line of, hey, I polled 100 people and asked them what candidate they voted for. And out of those 100 people, 200, or I can't remember what I said. If I polled 100 people, 60% said they were going to vote for candidate A and 40% said they were going to vote for candidate B, right? And so I am not predicting. I know I asked and I have the sample and I looked at it and I know it's 60-40. And then I'm analyzing to say, what does that mean? What does that mean as far as what other people voted or things like that, right? So probability is predicting future events. Statistics is analyzing past event data to then try to make inferences. That's the name of this block, is statistical inferences, is based on statistics, what kind of inference can I make? Which is a real mathy way of saying educated guess, right? And so in a weird way, I like probability personally, even though I have degrees and some other things that would say otherwise. I like probability more than statistics because statistics is more real, right? Probability is more a theoretical mathematical. It's like calculus. The derivative of x squared is 2x. It just is. That's a fact because we made it up to be so, right? What gets messy and hard with calculus is then when you say, how do I apply that in the real world, right? That's kind of the same thing between probability and statistics, right? The probability that the coin is going to be head is 50%. So that's just the theoretical truth that we have made it to be. Statistics can be not harder, but it is a little bit more challenging for someone like me to wrap my mind around, because we never can say in statistics something is true. We're doing statistical inferences so we can make statements like, I fail to reject this hypothesis, which basically says, based on my statistical evidence, the statement you've made, there's a high probability that it's true. Or based on my statistical evidence, it seems like you are wrong, right? And so we use statistics to make as strong of a statement as we can about things. It's like, again, going back to the voting, right? When people on TV say, we are calling the election for candidate A, what they are really saying, if you read all of the small print, is saying, based on our statistics and the number of people we asked and the response they gave, we are 88% sure that this person is getting 70% of the vote plus or minus 2%, right? They don't know anything for sure, but they have decided we have a high enough probability and a small enough margin of error that we can make this statement. And that's really what statistics are for. So with that in mind, let's go back to this idea of flipping a coin. So let me ask Jennifer, let me ask you a really hard question. You online? Jennifer?
Sorry, sir, can you repeat the question?
I didn't even say the question yet. I just was making sure you're online. So I said I was going to ask you I just said it was going to be a very hard question. So if I flip this coin, what percentage of time do you think that I should get heads?
50.
All right, outstanding. A in the course. You can take the rest of the semester off. All right. So Jennifer apparently does not know me that very well, and she assumes that I am flipping a fair coin. But that's fine. Let's assume for the moment that I am not a liar or a cheater, and say that this is a fair coin, and it comes up heads 50% of the time, and it comes up tails 50% of the time. So now let's say that I flipped the coin 4 times. So, Devin, you online?
Yep, I'm here.
All right, so if I flip this coin 4 times, how many times do you think it's going to come up heads?
2 out of the 4 times.
Okay, turns out you're wrong. I flipped this coin 4 times, and I actually came up with 3 heads and 1 tail. So how about it? Do you think I'm still a good person, or do you think this is a rigged coin? What's your call?
I think we should flip it a couple more times to figure out.
All right. I appreciate there's 2 things in there. One, I appreciate that Devin hasn't jumped to the conclusion that I'm a degenerate. It would have been a fair assumption based on other parts of my life. But he's basically saying, I am not ready to go to the police just yet, because he's saying, I'd like to see more coin flips. Because basically what he's saying is, just because I got 75% heads and 25% tails doesn't necessarily mean that this coin actually comes up heads 75% of the time and tails 25% of the time. Because even though he might not be able to express it in a mathematical proof, his gut is telling him, hey, it is not impossible that if I flip a coin 4 times, that I get 3 heads and 1 tail. Not only is it not impossible, it's actually not unlikely, right? With just flipping it, it's the same idea of saying if I flip a coin once and I get heads, that doesn't mean that it comes up heads 100% of the times. It just means that in that sample, that was what I got. And what he then said additionally, which is also important, is he said he'd like to flip it more times. So he is saying that I would like to see a bigger sample size, right? So if we wanted to be more articulate and clear with our words, what we're really saying is, hey, this up here is what I am proposing the truth is, right? You guys came into my casino and it is very boring. It's called Lieutenant Colonel Richard's Coin Flipping Emporium, and the only game we have is flipping coins. And it's all based around the fact that I said, hey, I promise these coins are fair, which means that I am saying it's heads 50% of the time, tails 50% of the time. What we did right here was we took a single sample and we got a point estimate, right? And so our estimate is 75% heads, right? So from a single estimate, or from a single sample, we got this point estimate that actually it's 75% heads. And what Devin is saying is, look, that's one estimate, but I don't know how accurate that is. So I would like to flip the coin more times. Either I would like to do another set of 4 and see what I get and maybe do more sets of 4, or rather than doing 4 at a time, I would like to take a bigger sample. So we can get a better estimate by either taking more samples and making more estimates, or by making our one estimate better by making our sample bigger. We're going to get into more later today and Thursday, kind of the math of why that's true. But is there anyone who that doesn't sit well with your gut? Does that make, on a kind of base level, does that make sense of saying, yes, if we flipped more coins or we did this experiment more often, that we could get a better estimate? Does that at least make sense at a base level, or is that bothering to anybody? Okay, so let's look at rather than coin, let's look at another example. So let's suppose that 52% of the U.S. population is men. I meant to change that from U.S. To Colorado. So let's say that's Colorado, because I did this example and then realized that doing this in R with 350 million people, that my little USAFA laptop was not up to that, and I did not bring in my gaming computer today to crunch bigger numbers. So we're going to assume that we're talking about the Colorado population. Okay, so, and I'm going to take a n person sample to calculate it, right? So so let's go back over before we talk about vocab. Let's go over to my R, right? So I've not posted this yet just because I got busy this morning, but after class today, I will post my slides as well as this code onto my instructor folder if you guys want to look at it and play with it. But this first part right here is saying I'm going to basically the R equivalent of putting all 6 million, there's about 6 million people in Colorado, and I'm going to put all of their names into a hat, right? So that's what this is doing here, is I'm making a variable that's called population, that's just a list of words, and 3.12 million of those words is going to be the word man, and 2.88 million of those words is going to be the word woman, to represent exactly 52% of the population is male and 48% of the population is female. So I'm going to go ahead and run that, and my computer is going to think about it. And so this represents the actual population, right? So I now have the exact population where the truth is that 52% are men and 48% are women, right? Now what I'm going to do down here is I'm going to take a sample, right? So this says draw n people. So I'm going to start off with n being 5,000. So I'm going to take a random sample of 5,000 people, because that's what this code does right here, is it says look into that list, which is 52% men and 48% women, and draw out n, in this case 5,000, random pieces of paper that have those names at it, and put them in this list, sample.people, right? So sample.people is just going to be a random sample of 5,000 people from Colorado. Then the last step is I said, hey, look at that sample and count how many of them are men, and then divide that by 5,000 to get what the percentage that are men, right? And so when I run this, I get a number, 0.4996, right? So let me ask Audrey, I can't talk. Are you online?
Yes, sir.
So does that, I got 49.96%. Does that mean that the actual percentage of men in Colorado is not 52% and is in fact 49%? Is that what that means?
No.
Okay, what does that mean? How did I get 49% if the real percentage is 52%?
Because it's like, this is an estimate of the male proportion.
Exactly. Okay, so Audrey just nailed it, right? So because this is a estimate, right? So here, you know what? Let's go back and look at some terminology so we can use the right words, right? So in this case, P is the usually the character we use for what's called the parameter. So the parameter is what describes the actual proportion in a population, right? So in this case, P is equal to 0.52 because that is the actual proportion of the population, okay? So that's P, the parameter. What we just calculated and what Audrey is talking about is P hat. That's how we read this right here. That is read P hat. So P hat is a point estimate, and we call it a point estimate because it's basically I took one sample and I said, here's my one guess, right? Other kinds of estimates would be I'm going to look at a bunch of different things, or I'm going to look at more than one sample, but a point estimate is basically said, hey, I took 1 point and this is my guess, right? This is my estimate. And so a P hat is the point estimate of P, hence why it is P hat. This is a statistic, right? So whereas P is an actual parameter because it's the real deal, P hat is a statistic because it's saying I took a sample and then based on that sample, I calculated the proportion of that sample. And so this is a P hat is a estimate of the parameter because the parameter is the actual proportion of the population. P hat is an estimate of that parameter. based on the proportion I get out of a sample, right? So what we just calculated was p hat, and our p hat was based on a particular n, a sample size, right? So I only, in the sample we did here, I only sampled 5,000 people, right? Which maybe 5,000 is not a lot. Maybe it's too much. We'll talk more about that on Thursday, but it definitely has an impact, right? If I said, if I make this, let's go, Ryan, are you online? Oh, he said it was going to be harder to get rid of him, but apparently not that hard. I already got rid of him. No, Ryan? Going once, going twice?
Yeah, I'm here.
Okay. We're going to go with, I was talking to Klein, but yeah, no, let's go with Zigros. Okay, so Ryan, what do you want to make my sample bigger or smaller?
Let's make it bigger.
Okay, so we're going to go from 5,000 to 50,000. If I make it bigger, do you think my estimate is going to be better or worse?
Better.
Probably better, right? Because if I run that, yeah, look, now I'm getting 52.376. So not only is it better, but if I keep taking, every time I run this, I'm taking a different random sample of a different 50,000 people out of that 6 million, right? And so not only is it better, but every time I run this, as you guys can see, it is none of the times do I get an actual 52%, but it is never too far off from it, right? And so this is another important aspect of the taking a point estimate. Going back to here, it's what we call the sampling error, right? And so the sampling error is how much the proportion statistic, that p hat, varies between samples. And so as we'll see more of the math of it on Thursday, but in general, Ryan's exactly right that when I increase my the size of my sample, it's not just that the estimate gets better. What really is important is that the variability is lower, right? Every time I take a sample, I am more likely to be close to the actual number. It does not vary as much, right? If I make this sample size smaller, like let's go down to 500, right? I am still getting within 50%, but now it is a bigger variation. Now I'm at 55%. Now I'm at 56%, 53%, 57%, 53%, all the way back down to 49%. And so as I make that sample smaller, I have more variability. It's like when we looked at that original coin flipping example, right? When I'm only flipping 4 coins, my only options are 25%, 50%, 75%, or 100%, or I guess 0%, right? And so it's going to jump back and forth between those. Whereas when I have a bigger sample, I'm going to have less variation around the actual number. And so that is one of the important reasons why sample size is important. Okay, before we move on to any other examples, any questions about these terms here and how they apply, at least conceptually, to what we were doing over in the R code? Okay, so we've established that P is the parameter that is the real actual proportion of the population. Looking ahead, that's the thing we usually don't actually know, right? That's the thing I want to know. And usually we don't know it. Here I've told you, but as we get into it, we'll see the idea is if we knew that, I wouldn't have to do p hat, right? Because the whole idea of p hat is to estimate p. If I really do know p, then I'm done, game over. I don't need to estimate it. I have the exact answer, right? And so we don't usually know p. We are trying to figure it out. And so we're going to talk a little about that now. But that's usually the thing we don't know. P hat is our estimate. And so going back over here, I'm going to up this. Let's up this back to 5,000 and say, okay, there's my estimate. Now, if I go down here, this next block of code, what this is going to do is this is going to take that estimate a bunch of times, right? So this line right here is just saying, hey, I'm making an empty list with 1,000 spaces because I'm going to start putting numbers in there, right? And so I'm going to say I'm going to take 1,000 samples of n people. So you can look at this loop here on your own. It's not as important that you guys understand how loops work right now. But what this is doing is it's saying, hey, for 1,000 times, what I want you to do is do what we did up here, right? This code is this up here. So it's basically saying, take that population of Colorado, 6 million people, and grab n random people, and then make an estimate of the proportion of men by looking at in that n people, which right now we're making n 5,000, how many are men, and then figure out that proportion. But unlike before, it's going to say, I'm going to get that number, but then it's going to say, store that number in my list up here, and then do that again. So I'm going to generate 1,000 estimates, okay? So I'm going to take a sample of 5,000 people, and I'm going to do that, and I'm going to make an estimate and do that 1,000 times. And then once I have all of those, I'm going to chart my results, right? And so if I run that, it's got to think for a second because it's drawing 5,000 people 1,000 times. So that's about 5 million people it's got to look at. So give it a second here. And then we get this result right here. And so on the x-axis are the ranges of the values that I could get for p hat, right? And then the y-axis is how often I got each of those p hats, right? Because I calculated 1,000 different p hats. And like Audrey said, my p hat is going to be different at different times, right? So let me ask, who do we got on here? Brooke, you online?
Yes, sir.
So just looking at this, is there any aspect about this histogram that jumps out at you that seems important? And I'm up for anything. So is there anything on here that seems to stand out to you?
Seems relevant that most of the data is coming out at 0.52 for the proportion of males.
I agree. So that is one of the big things, right? Is that when we did this, the highest frequency values are clustered around 0.52, right? Which on a gut level makes sense, right? Because the actual parameter P is 0.52. And so we would expect P hat to be close to 0.52 most of the time, right? But like I think it was Devin who said earlier, we've got also kind of like that coin option. It's not to say we can't get other values, right? We've got values as high as looks like above 55% and values all the way down to 50%. So every now and then we do get a sample that is a good deal lower than the real parameter, and we get estimates that are a good deal higher. But when we took estimates over and over again, the majority of them were clustered around 52%. Yeah, Cameron, what do you got?
Sir, is there a people object somewhere? Like how, is there a data?
Yeah, that was,
people.
You mean where we're drawing them from?
Yes.
Yeah, so that was, I maybe went over it too fast, but that's right here, right? It's just the population. So here is what we did, where we made a perfect population where we said, hey, there's 6 million people in Colorado and exactly 52% or 3.12 million are men and exactly 48% or 2.88 million are women. And so that was me simulating putting everyone in Colorado's names in a hat that we could draw from.
Gotcha. Okay,
Cool.
Thank you.
Definitely. Okay, so So Brooke says, yes, they are coming around there. Most of them are coming around. The actual parameter are of 0.52. Let me ask Holden, you online?
Yes, sir.
Do you have what can you tell me about the shape of this? Does the shape of this look completely random?
No, sir. It looks, was it unimodal?
Oh, I like that, unimodal. Yes, it looks unimodal. Specifically, if you had to describe it like one of our distributions, what does it look like as far as shape?
Normal.
Normal, yes, I like it. And I'm going to assume that when you say normal, you mean actually a normal distribution, which I'm just going to warn all you guys ahead of time. Please, for the rest of this class, if you use the word normal, only use it if you mean bell curve or normal, because I've had several people who will say, it'll be a straight line and they'll say, yep, that line looks pretty normal. And I go, whoa, no, in this class, normal means bell-shaped. It does not mean it looks like a ordinary straight line. So be careful using the word normal. But in this case, Holden's exactly right. This distribution looks very normal. And we're going to get into Thursday that not only does it look normal, it is normal, right? So I only took 1,000 samples here. If I took 10,000 samples or 100,000 samples, this would continue to look more and more normal, right? I actually, last in M1, we tried to up it to 10,000. And it took a good 8 minutes for my computer to do it. So I'm not going to do that again because I don't want to melt my computer. But the point is that this is called a sampling distribution, right? And so if we go back over to what we were looking at here, if I said I want a sampling distribution of n equals 100, which means I'm going to, every sample I take is going to have 100 people in it. And from that 100 people, I'm going to count how many are men or how many are women, and I'm going to get a p hat, an estimate of my actual parameter, which I know to be 0.52. If I do that over and over and over again and make a histogram of it, it is going to look more and more normal, right? And this is going to be, like we said, the x-axis represents all of my sample values of p hat, right? So this 0.4 here represents that, and this little bar above it is representing that when I take a sample of 100 people, a few times I get that 40% of them are male. This little bar over here says that more often than 40, sometimes when I take a sample of 100 are men, right? But by and large, when I look at how often I get each estimate, that the estimate I get the most often is 0.52, right? Because that's the actual parameter, right? And so if I take samples over and over and over again, and I calculate my point estimate is always that. It's an estimate. It is almost never going to be exactly right. Sometimes it will be, but as I take the estimates over and over and over again, over time, I am going to see this distribution that is centered around the actual value. That's what this means right here, right? If I were to take more and more and more more and more samples and calculate a point estimate from each one, the expected value of all of those estimates is going to equal the actual parameter, right? And that's what we're going to talk more about on Thursday, is not only is it going to go to there, but this is literally, if I do an infinite number of samples, it is going to converge to a perfect normal distribution centered around the actual value. And that centered around the actual value, that's the important part, because I'm getting into a little spoilers of tomorrow, but I consider this part 1 and part 2 of the same thing. Most of the time, I don't know this actual value, right? If I knew that actual value, I wouldn't need to estimate it. I would just already know it, right? And so this sampling distribution, I am showing you, this is what a sampling distribution is. We very rarely actually make a sampling distribution, right? Because if I go back over here to this sampling distribution, this is 1,000 experiments, right? And each experiment was a sample size of 5,000 people, right? So I sampled 5,000 people 1,000 times, meaning I took a random 5,000 people 1,000 times. So 5,000 times 1,000, that means I sampled in total 5 million people. So let me ask, I don't know, let's see, who do we got on here? Cameron, you on? Or no, I'm sorry, I got two Camerons on here. I'm talking about Scheidler. You on?
Yes, sir. I'm here.
So do you think that is a good use of my time to do to sample a total of 5 million people to get this distribution to see, oh, looks like it's centered around 52%, so it's probably 52%.
I'd probably say no. I think that'd be too much work.
It's too, well, because how many people did I say are in Colorado?
Not the 5 million.
Yeah, well, it was 6 million, right? And so I'm basically interviewing 5 million people to get an estimate of the actual proportion of 6 million, right? And so it seems like I'm doing an unreasonable amount of work because I could just, with a little extra effort, I could just do a census of all 6 million people and have the exact answer. Shoot, if I just, instead of doing 1,000 random samples of 5,000 people, if I just did a random 5 million people, then I'm going to be pretty darn close to my actual answer, right? And so we do this, we show this sampling distribution, not because we normally do it, but just to make the point of what would happen if we did it, okay? So stick with me because this is where I lose a lot of people. What a sampling distribution is important because, not because I actually do it, but to show what would happen if I did it, right? So the whole point here is, if I were to take a sample of 100 people over and over and over again, an infinite number of times, it will look like this. It will end up being a normal distribution that is centered around the actual value. Any questions on that? Do you guys, we can talk a little bit about the math on Thursday, but do you guys understand what is happening, what the sampling distribution is, and that if I sample over and over again and look at all of my estimates, that it will end up looking like that? Okay, so that's what happens if I were to do it an infinite number of times. Like I said, in general, we never do that. What we do instead is saying, I don't know what that number is, right? And so, but maybe I think it's that, right? So the way this normally pans out, and this is being very general, but this is really the remainder of the course, is basically works this way, is you say, hey, I don't know what the proportion of men in Colorado is, but I think it's 52%, right? And so you say, hey, I think it is 52%. And then I tell you, okay, if it is 52%, then I know that my sampling distribution would be distributed this way. We haven't actually made a sampling distribution, but I know that if the real parameter P was 52%, that this is what it would look like. Then you take a single sample and make a single estimate. And so let's say you take a sample of 100 people and you calculate that P hat is 0.4, right? And so then what I say is, well, if the real parameter was 0.52, then the likelihood of you getting 0.4 is down here and is very low, right? You could, as we said, you could get 40%. It's possible that I ask 100 people and none of them are male, right? I could get 0, but it is very low, right? And so I look at this and say, if this is the real value, then this is what the sampling distribution should look like. And so you take a single estimate and you get this value, it is very unlikely that you would get this value if this is the real value. And so this is how statistics work, is that you say, I think that the proportion, the real parameter is 52%. I say, okay, take an estimate. You take an estimate and say, the estimate says it's 40%. And I say, if the real value is 52, there is a very small probability that you would get 40. Therefore, I think you're wrong about the 52%, because it's possible that it's 52 and your sample, your estimate was 40, but it's very unlikely. It's more likely that you were wrong about 52%, and we go back to the drawing board. That is really the crux of everything we're going to do for the rest of the semester, is saying, hey, we're going to take what we know about sampling distributions and say, if this is the real value, I know what the sampling distribution should look like. So then when you take a sample and you get a point estimate, I can tell you what is the probability that you would get that estimate. And then based on that probability, because if you say, let's do this again, and you say, hey, I think it's 52%, and you go, okay, well, I took a sample and I got 0.51. I don't say, well, then you must be wrong because you said it's 0.52 and your sample is 0.51. What I do is I look over here and go, well, if 0.52 is right, it should look like this. You got this value right here. Yeah, that looks actually, if it was 0.52, there's a good chance that you could get 0.51. So that seems legit. It seems like you could, that there's a good chance that you are right. And so that's the whole idea, is saying, make a hypothesis, take a sample, and then looking at the sampling distribution, decide how likely or unlikely it would be to get that estimate if your hypothesis was right. Okay, I kind of started to jump into the next lesson, but how are you guys feeling about that? What questions you guys have? And we're trying to focus on the concept here. Is there anything that I was using that was not clear language? Can I re-describe something? Is there an example that would be helpful? What do you guys need? Okay, I'm going to take that hopefully as good feedback. Okay, so two things that are on this slide that we didn't talk about too much are sampling error and bias. So bias is more of a is less mathy, and it's more of how we pick our sample, right? So I have been over here, like Cam was saying earlier, the way I was truly randomly selecting people, right? I literally put everyone in Colorado in a hat, and I did a complete random selection, right? But the way we do random samples in the real world is not always like that. I have to actually interview people or do things, right? And so I am limited in how I can take my sample. I can't just, if I have to ask everyone, I can't put everyone in Colorado in a hat, because then if I got to drive to them, it might cost too much money, right? And so I want it to be as random as possible, but I can still, but anything that makes the estimate under or overestimate counts as bias. And so we can't always eliminate all of it, but we try to do our best. Like, for example, what I have here is, if I was trying to figure out what percentage of Colorado was men, I might say, well, hey, I'm here at USAFA. I'm going to just take a fully random sample of the cadets here. And that's fully random, but it's actually introducing bias, because men are overrepresented in the USAFA wing, right? We have the percentage of men to women here is not the same as the percentage of men to women in the Colorado population or the overall US population. So if I took my sample from USAFA, I would get a p hat that is overestimating the actual p. And so that would introduce bias. And so we try to avoid that when we can. Sampling error is something that can be gauged a little bit more, because sampling error is how much variability we have between samples, right? And we saw earlier in the class up here when I was taking my sample, right? When my sample size is n and I take the samples, all of my estimates are pretty close to 52%. So there's not a lot of or even if I didn't know it was 52%, they're close to each other. There's not a lot of variability in my estimates. But if I make that sample size smaller, let's say I'm only going to take a sample of 50, and I started doing those, but now I've got 62%, and then my next one is 54%, and then 56%, and then 50%, and then down to 44%, and then back up to 50%, right? So when my sample size is smaller, I get much more variability. And so that's not necessarily good or bad. It's a trade-off, right? Because I could say, okay, well, then I definitely want a bigger sample. 5,000 is better, which means 500,000 or 50,000 is even better, and 500,000 is great. And bigger is better, but at a certain point, my sample size is getting so big that I'm getting close to just asking everyone, and the whole point and value of statistics is that I can find something out about a large group by only looking at a small group, right? That's the whole value of statistics. If we could look at the whole group, we just would, and we wouldn't have to estimate. Statistics is saying, what's the smallest group I can do so I can save money and time to still get a pretty good idea of it, right? And to give you a preview of why that sample size is important, this is kind of looking into tomorrow. When we look at the central limit theorem, that SE on the right, so we already saw this right here, right? That as we take a bunch of p hats, the expected value of the p hats is the actual p, right? So the center of our distribution is the actual value. But then this right here, the standard error, this is the measure of variability of how spread out. The standard error is like the standard deviation, and it is equal to the, you don't have to memorize this right now, but it's the square root of the actual parameter times 1 minus the parameter. So in our case, that numerator would be 0.52 times 0.48, but then divided by n, the sample size. So the bigger the sample size gets, the bigger that denominator gets, and that standard error is smaller and smaller, right? And the standard error, going back to here, standard error is going to tell us how narrow our sampling distribution looks like. So if I have a bigger sample size, my distribution is going to look something like that, right? So now when I get an estimate, I can be more sure about whether that is a good or bad estimate, right? Because over here, if I get this number, I go, well, I don't know. When I look over here, that's a pretty high probability. I don't know if that's close to 0.52, but here, if I do this, then that's going to be 0.52 here, and it's only going to maybe go to 0.5 and 0.54, and there's still very small probabilities over here. But now if I say, hey, I get a p hat, and it's 0.55, if I have a bigger sample size, I am more sure that there is a low probability that you're going to get that, because my sample size is so big, there is a smaller probability that I would vary off as much as that. And so that's where the sampling error and variability comes in, and why sample size is important. Okay, we're going to do a review of this and then introduce the math of the central limit theorem on Thursday. Any lingering questions on things that I could have explained better, or questions that you have now, or things that you think I would be good for rolling in on Thursday, either as concepts or examples that would maybe help drive this home a little better as I lesson plan for them. Okay. Like I said, this week is more on the concept than is math, so I really want to make sure you guys understand, because I am not joking when I say the rest of the semester is about this. And so if you understand this concept, the rest of it will make so much more sense. So look at the lessons between now and Thursday. Bring any questions that you have so that I can answer them. But in the meantime, if you are tracking it, take your the extra time you have to try to knock out as much of this week as you can, so that as we get into more computational stuff next week, you got more free time on your hands for that. Okay, you have 120 seconds of class left, but I am a benevolent overlord, so I'm going to give you all of those 120 seconds back to do with as you please. Feel free to take a power nap before next lesson. But if I do not see you guys before then, I will see you guys on Thursday. And remember, I am busy today and Thursday teaching all day. So if you need the send me an invite for Wednesday or Friday. Otherwise, I will try to answer direct messages as I get. All right. Go away. I'll hang out if you got a question. But otherwise, I will see you on Thursday.
Thank you,
Yes,
sir.
sir. Regarding the makeup GR, I know that you said you didn't, like, the time frame isn't exactly set, but will it be similar format?